need to apply all our knowledge of sampling distributions and bias and variability to talk about the central limit theorem. The central limit theorem says, and really it says this, it says as the sample size increases, the standard deviation decreases. And just to be a little bit more specific, it says that the standard deviation in the sampling distribution decreases. And more so than that, so we have our normal calculations that are right over here. We used to use normal calculations where we had a mean and a standard deviation. But when our sample size increases, we have a new standard deviation. And I think I can see that as the sample size increases, as n increases, that this whole fraction is going to decrease. I'm going to have a larger number in the denominator, which is going to make the entire fraction get smaller. So let's do an example. We had previously done this example where we were looking at IQ scores, and so we had things that were normally distributed with a mean of 110 and a standard deviation of 25. We've done this problem before, so I'm just going to go through it fairly quickly. So we labeled 110. We're looking for scores below 90, so we labeled 90, and we shaded. We got out our formula, z equals x minus mu over sigma. We plugged in our values. X is 90, mu is 110, sigma is 25, and this gave us a z, that's 20 over 25, negative 20 over 25, which should be negative 0.8. The negative tells me I'm on the left-hand side, and the 0.8 tells me I'm not quite one standard deviation below the mean. So now to find this probability below 90, or that p-value, I need to get out my calculator and go to the normal CDF. Since I'm on the left-hand side, this is going to be a really, really small number to my standard deviation, my z-score. And when I do that, I get 2119. So the answer to this is, what's the probability in individual scores below 90? Well, there's about a 21% chance that one score would be below 90. So now, I changed colors. Okay, now what we want to do is apply the central limit theorem. So the central limit theorem says, let's up the sample size. So we're going to up the sample size to 5 scores. So the picture is going to look the same. The picture is going to be 110. We're going to put 90 on here. We're going to shade. The formula is going to be slightly different though. We're going to use an X bar right here because we're finding the mean of 5 scores rather than an individual score. Minus mu. And since this is using the central limit theorem, this is not going to be sigma. It's going to be sigma divided by the square root of n. So z equals 90 minus 110 over 25 divided by the square root of 5. So z equals, so I got to figure this one out. This is negative 20 on the top divided by, and the standard deviation was 25 divided by the square root of 5. Oops. And I move out of that parentheses. Okay, so that looks good. I got parentheses around my denominator. So I'm getting negative 1.7889. So when I take the mean, this 90 is even farther away. I'm more than one standard deviation away, which should kind of make sense because it would be hard for me to get an average of 5 to be that low. If I had an average of 5, those 5 should be randomly taken. They should be all over the place, and I would expect something that would be closer to this 110. So finding something that was less than 90 probably is not going to happen that much. So again, I'm going to find the probability, except this is going to be an x bar because I'm looking at the mean of 5 less than 90. And I'm going to use my normal CDF. So I'm going to do normal CDF. And I got a small number, negative 1 point, and I forgot what my value was here, 7889. I'm expecting a smaller percentage because I'm further away from the mean, 0.368. So for one person to have a score below 90, the probability is about 21%. But once I get an average of 5 scores, the probability goes down to about 3.5%. And again, that should make sense because I have extreme values. If I have 5 people, I wouldn't expect that all 5 of them would have a score below 90. I would expect some to be around 110, maybe some greater than around 110, and so I would expect something to have a mean that's closer to 110. That doesn't mean that it can't happen. This is 3.5%. That can definitely happen. It's just less likely. And if I up the sample size even more, then it'll be farther out on the distribution and it'll have less of a probability of happening. And that is how you use the central limit theorem. The central limit theorem, remember, it says that instead of having something normal with a mean and a standard deviation, that your standard deviation changes because your distribution is more compact.